This was the one which was worked out by Einstein, and which is the many things he did. I know he did the Brownian motion and Brownian diffusion, but this was the thing which was done somewhat later, and it's a brilliant way that he started. Somehow he got into his idea to study the probability of a fluctuation, and he introduced the concept that at system at equilibrium in the homogeneous state, it has two independent thermodynamic variables, and he worked out with and it played a very important role in the later destruction of hydrodynamics. That he, for example, he took temperature and pressure and worked it out, and that situation, isothermal isobaric, is the best way to do hydrodynamics, and he also did entropy and volume, these fluctuations, and then he found out the probability of fluctuation. The way we did that, he constructed a fluctuation and got the work done to this create that fluctuation, and from there he did the probability of fluctuation. Now, why do we talk of fluctuation? Okay, and what is the reason? We know that at equilibrium, free energy is minimum. So, now if the free energy is minimum, then if I consider, if I expand free energy as a function of, say, density, and I say my density undergoes a fluctuation around the equilibrium fluctuation. So, density is A naught, rho average plus delta rho. Then the way one writes is that free energy A naught at equilibrium rho average. Now, the first derivative of free energy with respect to density goes on like that. Now, this quantity, which is the derivative, because the free energy is minimum, this goes to 0. So, then I have, and I make that delta rho, change in free energy as a delta rho, then this also goes out. Then I can write as the first term of this Taylor expansion as so this will be just derivative, partial derivative, other things kept fixed. Now, then we can say that if I want to have a fluctuation, that fluctuation has this cost in free energy. That means to a small enough fluctuation, my free energy surface is harmonic. This is the rho average. Okay, is that clear? It is a very trivial logic, but at the same time it is very profound. So, these are the, then we call this quantity as the force constant of the fluctuation. So, you immediately see that this is the quantity which must be positive, so that there is a cost to free energy. Then if as in phase transition or chemical reactions, if there is a barrier and then there is another state here, Then to small, we say to small fluctuations, this is stable, but to a large fluctuations it goes over there. When it reaches there, this derivative becomes negative now. So either it has to, once it reaches there, it has to come back there or come there. So the equilibrium between the two such states characterized by minimum is determined by the difference in this, but dynamics is profoundly dependent by the oscillations here and the curvature there. Okay. Now we do not want to talk of dynamics, instead we want to talk about this quantity, that what is so this is the chapter you can read where talked about the fluctuations. So basic idea is that what are these fluctuations are the most important quantity, because this is the determines the response. The second derivative determines the response of the system to a fluctuation. How? That is the called the linear response or response functions. And these response functions are the most important properties of a system. Like when we brought the rock from the moon, other than the density, the first thing they calculated is the specific heat. Actually, when we go to many museums, they will write down the specific heat of that below, and the conductivity. Those properties, conductivity, specific heat, are the response functions. Why? Because if you so now, as I am telling you from the morning that this is a very important. If I want to change temperature by delta T, then I have to give a amount of heat delta Q. And so this is the relation. Cp, if you bring it here, then delta Q by delta T is the Cp. So specific heat is the amount of heat needed to change the temperature by 1 degree. That's what you have studied in 8th grade. At least we studied in 8th grade. Compressibility, now I bring here dVdP, then is the compressibility. That means the unit pressure, the pressure needed to change volume, everything by unit. And this is the magnetic susceptibility chi. It is connected to the polarization or the magnetization created in the system by applying this amount of external field. So every case we are applying an external perturbation. Here we are giving an amount of heat, here we are giving an amount of pressure, and here we are giving an external magnetic field. On the left hand side we are having the response of the system. And then these constant coefficients are the one which gives the response, the magnitude of the response. Near a phase transition, these response functions all diverge. Then a very small amount of perturbation create a huge response. Specific heat goes to infinity. Remember the lambda curve. Compressibility goes to 0. Gas liquid transition you can compressively. So then and these also diverges. So stability condition of a system, both mechanical, this gives you the mechanical stability and this you give the thermodynamic stability. Both the stability are connected with these quantities. So whenever we talk of a system is stable and non-stable, there is a set of stability conditions which is discussed in my book in a little later. I'll hope to get into that. So I hope I have impressed sufficient amount on you to tell the importance of these response functions. They are the most important constitutive properties of a system. Most important constitutive properties of the system. So And the ones, whenever any matter is, new things are created, these are the first properties that one measures to characterize the system. Okay. Now, so my next comment, and very important comment too, is that these are the quantities, these response functions. In addition, also, and this is the most fundamental relation, one of the things. In my book, first time I have the chapter 6, I had fluctuations and I said realization of the promises. Later my students said they noticed that is a bit too much. But the whole statistical mechanics is quite a formidable structure, as you have seen. You have to go quite a bit before you start getting the results, which is somewhat different from quantum mechanics, because you start with Schrodinger equation, which is also a postulate, and then you start getting results which are connected to spectroscopy rather quickly. Not in statistical mechanics. Here you will get a huge amount of results, but you have to plow through certain amount of things. You have to understand systematically how. Just going to partition function is itself has this this process, and but then at the end of the day, much of these, for example, if you are going to do soft matter, you are going to do phase transition, you are going to do polymer, liquid crystals, everything is nothing but statistical mechanics. So you are going to put this extra, the nucleation, everything. You are going to put this, but at the end of the day, you are studying phenomena. See, I have again and again telling one thing, in chemistry, the way we do quantum, we don't study phenomena, rarely we study phenomena. We study numbers, which are then connected to spectroscopically. So there is a huge difference the way these two disciplines work. You go to a quantum chemistry conference here, at least in India, they hardly talk of, they talk of formalisms, they talk of second decimal place sometimes, but they don't talk of any phenomena. So their main delight is the publication in Jacks and Agavante. Okay. Now, so the important thing of these quantities here, my point I am going to make, most important point, are essentially the second derivatives of free energy, specifically with respect to temperature. This one is with respect to density or number or volume, and susceptibility is with respect to these external field. So these quantity, density, temperature, magnetization, these are external control parameter. We will introduce a term called order parameter little later. Okay. So to summarize this part, that these important things, specific heat, compressibility, these things are the second derivatives of free energy. First derivative is 0, and you can easily see why. Because if I give a small amount of heat or small change, I put a little bit of pressure, then since it is a minimum, how much it is going to displace is determined by this quantity, and then this is given by this, which is a spring constant. It is a harmonic surface, it is a spring constant. These are extremely important because these trivial, apparently trivial things are basis of theory of Landau's theory of phase transition. It is a wonderful theory that we will do. After this, we will do monatomic gas, then we will do diatomic, then we will jump a little bit, we will do Bose-Einstein later, we will go to Mayer's theory, interacting system, then we will go to Landau theory. So I'll do a little bit back and forth kind of thing. I'll not follow the textbook completely. Now, when you write a textbook, you are kind of constrained by the kind of established by Macquarie or all other people. So now, okay. Now, so I'm going to now do the next part. So this quantity is a very interesting quantity now. How do I get that? Okay, this is another very important response, that if I study this thing, even at equilibrium, even in the absence of an external perturbation, is the most important thing, the particles are moving. This is a very important language which our Rigo Kubo introduced, called the natural motion of the system. the system is undergoing continuously thermal motion. That thermal motion gives you diffusion dynamics, that gives you resistivity, that also gives you specific heat. Now I am making this far-reaching observation that these fluctuations contain the information of specific heat and isothermal compressibility. So natural motion of this system determines, and I am telling you I cannot overemphasize, it is so important. Here my student has done these fluctuations in total energy by simulation and volume, and you can see it is, as I was telling in the morning, they continuously fluctuate. They continuously fluctuate, they are just natural system. Remember, Castellan gave a wonderful example of, Castellan said, okay, I now and I have put some colored liquid here, which will now go into here, and say this is the up to this. So same level here, there will be a meniscus. But I make this pipe is very narrow. So this meniscus is visible in a microscope. So now I look at it through a microscope. I am a wonderful artist, as you can figure out. So now this height, I call this height h, and now I plot that h as a function of time. I will find that it is continuously oscillating without anything. It is an equilibrium with the atmosphere. So the reason is that there is a natural motion of the system, So the way, that is the nature's way or the system's way to interact with the external pressure. Okay, everything is at equilibrium. So I am in completely equilibrium, but my system is undergoing these fluctuations. It is very, very important to realize that this is a natural fluctuation. Okay. So equilibrium well-defined average values originate from thermal motion of atoms and molecules. This is from my book. Statistical provides the profound result that the response functions that I have discussed here in three things are given exactly by mean square fluctuations of respective conjugate thermodynamic properties. So I am going to now tell you what is the specific heat, how do we calculate specific heat, and what is the microscopic definition and microscopic meaning of the specific heat. Okay. And so this is the way we remember d dt is the specific heat. Okay. So I do the d dt, I go to this e, d dt I do, I bring one e, so it becomes e square. Another term comes from here, but q is again sum over e to the power minus e by kbt. So that brings it, so q right. So I take a derivative, it becomes 1 over q square, it becomes 1 over q square because it is in the denominator, and then I take the derivative, it brings a ei out, and there is one ei before here, so same thing ei by kbt, so this becomes a square. Now this square, but it has q denominator, so I put the q inside and complete this square, so that thing is just average energy square. This quantity on the other hand is this e square, kbt square, and by it is there kbt square both the two places, and then 1 over q, and so this quantity is nothing but e square. Okay, so I have e square minus average e square, exactly. So specific heat is then this quantity. So that's why the relation that E square minus, so this is specific heat CV, 1 over kBT square in both the two cases, I bring it upstairs, so I get kBT square CV, and this square is this quantity on the left hand side. So specific heat is nothing but mean square fluctuation of energy. This very simple thing, that's what in my book I had the original title, that realization of promises. This is really such a wonderful result which nobody anticipated. That specificity is nothing but mean square energy fluctuation. As I said, I cannot overemphasize the beauty and the importance of this relation. Okay. Now that I did a specificity at constant volume. Now I want to do specificity at constant pressure. Specificity at constant pressure will come from our NPT ensemble, and H, then it become E plus PV, we discussed in the morning, and then you can exactly play the same game and you find out that specificity at constant A is again mean square fluctuation in the enthalpy. Okay, that is CP. CP and CV can be quite different. Experimentally we work with CP, but CV is the one theoreticians work with. That reason is that the other one much in canonical ensemble is easier, and that's what we do all the time, canonical ensemble. Okay. Now I go into compressibility, again the same thing, that I go to the NPT ensemble and I again do the V square delta V, and you know dV dP here, dV dP I do here by P, and P here brings out a V square. So I get V square minus delta V square, which is the mean square fluctuation. Then dV dP is the mean square fluctuation in volume, and this is my compressibility. So I get the relation is that the isothermal compressibility is nothing but sigma V square, or here is the well-known relation. Important thing is that isothermal compressibility is given by mean square volume fluctuation. So that's why this was given here. This is the mean square energy fluctuation. This is the mean square volume fluctuation. These are real simulations of, I believe, of water. There is reason to talk of water, and I will talk about water in the context in a little bit in a greater detail. So compressibility we have done, specificity we have done, we have not done IA. So there is an exercise that you can easily do. This you have to do in the grand canonical. Grand canonical, you have to consider, you can do exactly same game you play, you know. But in the grand canonical, remember that we are screwing it up a little bit, having the same notation. But grand canonical, you can do the number fluctuation, right? And now you can write the compressibility, isothermal compressibility as a derivative. See, it is dV, then you write dV dP and replace V by density, N by V, and say I want the number fluctuation, not the volume to fluctuate. Then you will get D a D, and that means I have here in density I have N instead of volume, and this will be if you work it out, you will be able to get this result. The isothermal compressibility is the final value is the same. You can calculate in the grand canonical, you can calculate isobaric ensemble, two different things, two different way we calculate that. If we want to calculate in canonical ensemble, then I just do the volume fluctuation. Oh sorry, if I do NPT ensemble, I do the volume fluctuation. Because you know canonical ensemble volume is fixed, it doesn't fluctuate. But in isothermal isobaric, NPT ensemble volume fluctuates. From that fluctuation, I can get the mean square fluctuation, and that gives the compressibility. But if I consider that, as I told you, we discussed, this is difficult to do in a computer simulation. The N, that's done by Gibbs ensemble, and that's the bath that I'm not going to go into because I'm not very clear myself about it. So, one of the questions that was raised, why different ensembles have the same result? Okay, the reason is the following. Let me see if I have the graph here. The reason is the following, that now let us see the relative fluctuation. So, sigma E square this is the width. Okay. And this is also a question that was asked. So, we will come to that, answer both the two questions. So, remember when we do, we always talk, we need to talk of the relative value. Why you have to consider relative value? That because you cannot compare 100 with 1000 and you cannot compare 1000 with 10,000. Say we want to describe the distribution of salary in a concern. Then what you have to do? You have to find out the maximum salary. Now, in concern to concern, the maximum salary is changing. If you want to study the dispersion, you should better scale by that, make that equal to 1 and then see how the dispersion goes. Here also, so this is the relative fluctuation that we need to look into. And relative fluctuation, then sigma E square is CV, cavity square. So sigma E is cavity square by square root. I divide by then the energy. This scales as N because this is average energy. That's an extensive property. This scales as N to the power half because specific it is also an extensive property. So we have root over N by N. So it scales as 1 over root N. That's true everywhere. So the scaling of fluctuations. So now if I want to compare the results of canonical and grand canonical or canonical and isothermal isobaric ensemble, then the results will be the same when the fluctuations are small. So the fluctuations are these things that is moving around here. When N goes to infinity, these fluctuations, relative fluctuations become very, very small. They goes to 0. The fluctuations go to 0 as 1 over root N. This is the reason why whatever ensemble you study, you get the same result. This is also intimately related with the stability conditions that we'll discuss later.